Well, it's great to be here. And now, as I was preparing this talk, because it's taking place in a ping pong venue, I was trying to find some connection between Clojure and ping pong, and it was hard. But the only thing I could come up with is if you take a ping pong ball and you cut it in half and separate it, it kind of looks like two parens. So those aren't coconuts; those are ping pong balls. So what I'll be talking about today is simple ideas with huge impact from Clojure and Rama. And by simple idea, I mean an idea that you can articulate in just a few seconds. And by huge impact, I mean something that has a substantial effect on your ability to produce either robust software or just produce software at a much greater speed. Okay, so the first idea I want to talk about, this is actually not from Clojure or Rama, this massively predates it, is don't store state in global variables. And this goes back a long way. I actually found this passage from Dijkstra that he wrote in 1976, and I just wanted to read one sentence from it. He said, "If he discovers to his dismay that the value of one of these variables has been tampered with in an unintended and as yet unexplained way, he is in principle obliged to read all the code of all the inner blocks, including the ones that should not refer to the variable at all, for precisely there such a reference would be erroneous." So in a little bit complicated language, he is capturing the essence of what's wrong with global variables. To understand code locally, you have to understand code globally. In other words, code becomes coupled all over the code base, and you have spaghetti code. Now, what he was advocating for at that time wasn't to not use global variables. It was to be explicit about which global variables functions were depending on, which is an idea that did not really catch on. But he did get to the core of what's wrong with them. And ultimately, the effect this has is that if you use global variables, it just makes everything strictly worse. It's harder to understand the code. You're going to end up with more bugs or longer development time or both. Like, you're not gaining anything from using global variables. It's not a trade-off. It's just strictly worse. Now, you guys already understand this, right? Like, actually, most, if not all, programmers already understand this. So why am I talking about this at a Clojure conference? Like, this is a boring topic, right? And it should be a boring topic. And if you've read anything I've written in the past couple of years, you know where I'm going with this, which is that databases are global mutable state. And anything you can say about global variables, the same thing applies to a database. Except databases are actually even worse. First of all, they're concurrent, so that makes everything about 1,000 times harder. They're durable, so any mistakes you make just live forever by corrupting the database. Unlike a regular program, you can't just restart the database to get it back to a known state. You have to deal with the corruption, and probably you will not be able to fix it completely. And then the last thing is that your code, it's not just in one program. It's often spread across multiple programs, and oftentimes in different languages. Like, that's not even spaghetti code. That's spaghetti and meatballs code. That's really bad. Now, whenever I bring this topic up, inevitably someone says something like, "Oh, no, databases aren't the same as global variables because of transactions." But transactions have absolutely nothing to do with the issues of that global mutable state causes, of coupling code together and creating spaghetti code. They just don't address the core issues with global mutable state. And so it's an interesting situation in the industry in that most programmers understand that global variables are bad, if not all programmers. Like, we've progressed a long way since Dijkstra wrote that passage in 1976. But very few programmers understand that databases are the exact same thing. So it's just this giant industry-wide cognitive dissonance. Now, there can be very good reasons why you're using a database or have to use a database. It can be legacy reasons. It can be political reasons. It's certainly not technical reasons, at least not anymore. But you could have a good reason nonetheless. But what you should be doing is you should use it begrudgingly. Like, I think to begrudge as a programmer is one of the most powerful tools we have at our disposal. And honestly, there's so much self-inflicted complexity that we deal with on a daily basis. If you're not in a constant state of annoyance, you're doing it wrong. Okay, so the next topic I want to talk about is homoiconicity. And man, what a great idea this is. It's so simple. Just write your code as data and how incredibly impactful it is. And what it enables you to do is to program compile time just like runtime. It enables you to compose your programming language back on itself. And like the only way I can describe it is it opens up a new dimension of programming. And of course, we all know the first rule of macros is don't use macros. And that is absolutely true. You should not abuse them. But there are things that you can do at macro time that you just cannot do at runtime. And those are forms of expression and abstraction that are available in a Lisp, which just are not even available in other languages. And I actually just wanted to show one example of that, just because it's so cool. And it's so cool because of how invisible it is. But these are two lines of code that do the exact same thing. One of them is using Clojure core's getIn. The other one is using Spectre. They're expressed the exact same way. It's the same number of tokens, and it's the same arguments, just in a different order. And the difference between these is that the Spectre version runs 30% faster. Now, the Clojure core version, like getIn, is efficient. Like, it's doing what you'd expect. It's reducing over the sequence, and it's just calling get over and over until it gets to the final result. So the fact that Spectre is 30% faster on something that's already efficient is like pretty mind-blowing, I think. And the reason for this is because of what it's able to do with macros. And what this like demonstrates more than just the performance aspect is a broader point, which I think is really important. Like usually with abstraction, you add overhead. The more abstract thing is going to be slower. And Spectre, compared to Get, I mean, they're not even comparable. Spectre is like insanely expressive, able to do a tremendous amount of things. So the fact that it's so abstract but also faster is pretty crazy. And that is the kind of stuff that macros lets you do. And just broadly, the way this works is Spectre implements an inline caching and compilation system. So I'll just explain it at a high level. So select any is a macro, and it does a few things to set up inline caching and compilation. So first of all, it generates a var for the call site where it can store some state at runtime. And then the code here is a little bit different than the last example, just because this code has a local in it, which is dynamic and is going to change on every invocation of the call site. And that's the key challenge to actually getting this thing to work. So at macro time, Spectre analyzes the path, which is that first argument there, to determine what in there is static, like a keyword or a reference to a var, and what's dynamic, like a reference to a local. And it just takes that information and packages it up so it can be used at runtime. And then at runtime, the first time it comes to this call site, it doesn't have anything cached, so it's going to analyze that information it captured at macro time, and it's going to analyze the new information it has, which is what do these symbols here actually resolve to, because that determines how it interprets the arguments. And then what it ends up doing is it evals a new function that it's going to cache into that global var, and that function will very efficiently construct the path for all future invocations. So that the next time it comes to the call site, and the next million times, it just gets that function from the cache, calls it, and then executes it. And what this effectively does is, compared to the getIn implementation, this completely strips away that reduce that it has to do on that data structure, because we've already composed that function that we need through the system. So the interesting thing about inline caching, like this is a technique that's super common among language implementations in compilers. Clojure does it, the JVM does it. Like you see it in pretty much every language. I'm actually not aware of this ever being done at the library level before. And certainly Rich Hickey and John McCarthy, they did not anticipate someone building an inline caching and compilation system on top of the macro system. That's just something that falls out of it being just so uniform and general purpose. And the effect of this is that what macros let you do is it lets you mold the language to fit your application rather than having to squeeze your application into the same set of constructs that the programming language lets you use. And this is a really powerful thing. And this I'm going to repeat a lot during this talk. And if you don't take away anything else from this talk, just take away this. This is probably maybe the most important thing I've learned in my past 15 years of programming, which is that uniformity enables composition. In this case, the uniformity of program representation enables the composition of the language back on itself, and that composition creates absolutely massive leverage. Now, the thing about homoiconicity is that you guys are voluntarily attending a Clojure conference, so you guys already know this. But you guys know that when you try to explain Clojure to people who don't know Clojure and who haven't encountered homoiconicity before, you don't get a very good reaction. You get things, responses like, what's the deal with all the parens? And also, you yourself remember what it was like the first time you ever saw Clojure or Lisps. You probably reacted the exact same way. But somehow, you guys, and this makes you a very special slice of all the programmers in the world, were able to get past that hump so that you could see through it and see the huge value that homoiconicity provides, whereas you could not see that value before. So I want you guys to remember what that was like to get through that learning hump, and also what it's like to try to explain this to people who haven't gotten through that hump before, because I'm going to show you some more ideas in this talk, which are going to challenge you just like homoiconicity challenged you the first time you saw it. Okay. So the next topic is, the next big idea is using data structures for program state. And this was a big one for me that I learned from Clojure. Before I wrote Clojure, I would write lots of code like on the left, where, and this is typical of other languages, you define a class for every single concept in your program, and you define getters and setters and all these methods specific to that object. And this is in contrast to Clojure, where you would just represent it in a map, or you'd represent it in a record, which is basically the same thing as a map. And one of the operating principles of Clojure, and this is actually on the rationale page, is this great quote from Alan Perlis, where he said, "It is better to have 100 functions operate on one data structure than to have 10 functions operate on 10 data structures." And if you've used Clojure, this really resonates. This quote is actually, it's from an article that Alan Perlis wrote in 1982 called Epigrams on Programming. There's about 150 epigrams in there, and there are some real gems in there. And I actually think that Rich Hickey actually chose the wrong epigram to use as the basis of Clojure. I think he should have chosen this one: syntactic sugar causes cancer of the semicolons. But effectively, what this does, by just use data structures for program state, it just lets you reuse and compose so much functionality all the time. Instead of having to re-implement this stuff for these specific data types that you define, or arguably even worse, have to implement adapter interfaces to be able to make them interoperate, you just use them directly and you don't even think about it. It just streamlines stuff so much. And so this is another instance of this phrase. The uniformity of representation of programming state enables composition by just letting you reuse a language for all of your data, and that creates leverage by just streamlining things so much. And that brings us back to databases. And databases, in contrast with p-states, which is Rama's abstraction for durable indexing. P-states stands for partitioned state. And this is the battle between data structures and data models. So you look at a database. Every database has a fixed data model. So like key value, relational, document, graph, entity attribute value, which is the fixed data model that Datomic uses. And a data model supports only certain queries efficiently, just by the nature of it's fixed. It's only indexing things in one way, so there are only certain queries it can handle efficiently. And there's no such thing as being able to compose a graph database inside a document database. Like, these are separate tools deployed separately. It just makes no sense. But it turns out every data model is just a particular combination of data structures. Key value is a map, document is a map of maps, a graph data model, there's various ways you could do it. In this example, you would have one map for the node properties, another map for edges. If you wanted to be able to have the same edge between two nodes multiple times, or edge properties, you would use different representations, but it would be small variants of that. And then entity attribute value is just 4 maps. They're all sorted maps, and then the key is just different orderings of tuples to change how it's ordered, and that affects, and each map supports different kinds of queries efficiently. And this is how you would do p-states in terms of data structures, where Rama extracts the core primitive of data structures and use that directly, which lets you trivially implement any of these data models or any data model that you want to do that's not implemented by any database. So like on the top left is an example of declaring a key value data model with Rama. So p states in Rama are symbols beginning with $2 so this one is called KV. And you can see this is just a map of strings to longs. On the top right, this is just a value p state. So on this one, we're just storing a single long value per partition of the p state. And that one should be pretty mind-blowing because every database is based on the concept of a key, which means it's inherently map-based. But there's no reason that has to be the basis for a p state because you can just have anything. And there's tons of use case for just simple value p states like that. On the bottom left, this is one way you could do like the AVET index that Datomic does. You could do it the same way by literally just having a map of tuples, just like Datomic does. I actually think this is a better way to do it, where we declare it as a map of sets. And the difference between this is that you can get the sizes of those inner data structures in O of 1, whereas you would not be able to get the size of those with the way Datomic indexes it because they're all just in a giant list. So it would have to actually scan the whole thing to get you the count. What that subindex flag does in Rama, it just says that that inner data structure can be very large, and so the elements should be indexed on disk individually instead of the whole data structure serialized as a single value. But it doesn't actually change anything about how you interact with it. It's still a data structure. You interact with it in the same way. And on the bottom right is an example of a graph p state. This one's just doing everything in one data structure. Fixed key schema just means it's a map with a fixed set of keys where every key can have a different schema. As you can see, it's storing node properties in one, or storing the properties in the, as an inner map for the props key, and for the friends key, it would be a set of other user IDs. And one of the effects of just defining your durable indexes as data structures is it lets you, again, just reuse and compose all the functionality that you already have. They're just data structures, so all this stuff just works directly. And then also, it just, the other thing it accomplishes is it lets you do any data model because data structures are inherently composable. You can have any combination of data structures you want. And when you use Rama, what you do is you make as many p sets as you need and as many different shapes as you need to support all your query needs. And what this lets you do is kind of like how Clojure lets you mold the language to fit your application, Rama, through p states and data structures, lets you mold the storage to fit the application rather than having to fit every single feature application into some fixed data model, which always creates impedance mismatches. So again, it's another instance of this saying, the uniformity of the specification of indexes as data structures enables composition in two ways. One, in that you can compose data structures to make any data model you want, and then the other way it supports composition is by letting you reuse the functionality you already have for interacting with data structures. And this creates just absolutely massive leverage. Okay, so this brings me to the natural next topic, which is navigation. And this is the abstraction implemented by my library, Spectre. And the idea behind navigation is to have a more composable way to just interact with data structures, either for querying or for transforming. So I'm going to motivate this through a few examples. And the first example is a really simple one. We're just going to take a list of numbers, and we want to transform it to increment the last odd number. So I chose this example very intentionally because it's not a nested data structure. There's a big misconception that Spectre is just for nested data, but that's not the case at all. What it fundamentally is about interacting with data structures in a more composable way, and this is really useful even if your data structures have no nesting whatsoever. The second example I'll give, this is a nested example, so this is to increment all the odd numbers in a map vector of maps of numbers. So the code to do the first example in Clojure would look something like this. So you have a function to increment the last odd number in some sequence of data, and so it iterates over the data to find what's the last index that has the odd number, and then if we found something, we update the index at that position to increment it. And this works, turns out it works on a vector, but this code actually doesn't even work on a list. You would need a completely different implementation for that. And actually to get it to be high performance in both cases is somewhat challenging. And with Spectre, it looks like this. So the idea behind navigation is to break up the problem and to separate what you're trying to do with where you're trying to do it. And every Spectre operation revolves around this idea of a path, which step by step navigates to the values of interest inside whatever data structure you're looking at. And so what this path right here says, first it says navigate by filterer odd. And so that navigates to the filtered view of the sequence by filtering by odd. So that's the same as running filter odd on the list. And what filterer does is it remembers, it navigates you to the filtered list, but it remembers the original locations of all those values in the original list. And then we navigate to the last element of that filtered list, which will be the last odd number. And that only navigates if the list has anything in it. And then this is wrapped in a transform, which says we're going to change the original data structure by taking any values we navigated to and incrementing it. So what this does is it increments the last odd number, and then this works on vectors and lists, and it greatly simplifies the code for actually doing this, because you're able to break it up into these small pieces that each do one thing well and just compose them to solve your specific problem. And you can think about Spectre as similar to like the Unix philosophy, right? Of having all these small programs that do one thing well, and then you express the specific behavior you need by composing them. In the case of Unix, by piping them. Unix is all about just passing strings between programs, whereas Spectre would be about passing data structures. But the same idea. You have a bunch of navigators which each do one thing well, and you express your behavior by composing them. And Spectre makes the composition absolutely trivial. Okay, so let's look at the second example, incrementing the odd numbers in a map of vector of maps. And this is how you would implement it in Clojure. So because we're going to have to navigate to map values twice, so I factored out a function map vals. I bet everybody in this room has implemented this function before. And so this is a pretty good way to implement it. And then to actually do our specific transformation, you call map vals, and then you have an anonymous function, and you call map v, and you have another anonymous function, and then, and then more nesting to get your result. And this code is, I hate looking at code like this. Like, it's absolutely unreadable. And with Spectre, it's completely trivial. It's just navigation. So map vals is a navigator that goes to all the values of a map. All goes to all the values of a sequence. So it's map vals, all map vals. You filter on odd numbers. You wrap that in a transform. You do an increment, and that solves the problem. And on top of that, this is way faster than this code as a bonus. OK, I'm going to show one more motivating example, just because I just think this is so cool. And this is a recursive example. So here we want to take a tree represented using vectors, just nested vectors, and we want to reverse the order of all the even numbers based on a depth-first search. So you can see the 10 swaps with the 2 and the 4 swaps with the 8, and they're at various levels of nesting. So just imagine writing this in Clojure manually. It's not obvious how to do it, and you're going to end up with a big function that's very specific to this problem. But with Spectre, you think about it differently. You think about, how can I break this up into smaller pieces and accomplish my goal through composition? And so this is a solution with Spectre. And that's what tree values does. Tree values doesn't solve the full problem of reversing the order of the even numbers. It just solves the small problem of how do I navigate to all the values of a tree. And the rest of it is going to be accomplished through composition with the navigators that already exist. So tree values is defined as a recursive path. So it's just a path that can refer to itself. And all it's saying, if we're navigating to a vector, then navigate to every element of the vector and recurse. Otherwise, stay, because we're at a leaf node, and that's what we're looking for. And then to actually solve the specific problem, tree values even navigates to all the even values of the tree. What that subselect does is it navigates to all those values as a list, right, as a single list of just those even numbers. And then we just call Clojure's reverse function from Clojure core. And subselect, kind of like what we saw before with filterer, it remembers the original locations, even though they're at various levels of nesting, and it reverses them in the original locations. So, I probably wrote this for the first time 8 years ago, and it's it still makes me happy to look at this. It's just it's so cool, it's so elegant, and it's just so powerful to be able to do stuff like this. And the cool thing about doing it like this is now we didn't make something to solve the specific to solve this very specific problem. We made this tree values navigator, which is just solves a more specific problem, but in a reusable way. And so we could use tree values to do other things, like put in a select to actually just select all the values of the tree, or you could do a different kind of transform, in this case, converting them to a string. So this is really powerful. Now, to say Spectre has been controversial within the Clojure community is an understatement. People say things like, Spectre is useless because you shouldn't be nesting your data that much in the first place. But that's not the point of Spectre. The point is a composable way to interact with data structures. It really has nothing to do with nesting. It just happens to be really good at nesting. And all I'm going to say about this is, again, remember what it was like the first time you encountered homoiconicity. You were confronted with one of the greatest programming ideas of all time, and you could not see the value in it. It's incredibly impactful, but it seemed useless to you. The exact same thing applies to Spectre. Now, Spectre has been a really interesting library for me because I originally built it for a very specific need, which was I was implementing the Rama compiler. And the Rama compiler has to do all the same sorts of things that the Clojure compiler does. In Rama, you have an abstract syntax graph, which is a little bit different than Clojure with the abstract syntax tree, but basically the same idea. And then you can have anonymous operations, which would be like a node in your graph, and that would have embedded within it a subgraph for the code for that operation. So it's a pretty complicated data structure, and I just needed a way to query it and manipulate it and transform it in a sensible way, and also in an immutable way. And what happened to me with Spectre is, as I kept using it, I started seeing how all these different problems everywhere could be decomposed into navigator problems, into these small pieces of reusable functionality. And inevitably, I do end up reusing those things over and over. So it really changed the way that I look at programming and how when I look at any sort of interaction with the data structure, I see it in terms of the composable components instead of just this one big messy problem that I have to solve. Now, the cool thing about Spectre is that the core of it is insanely simple. All it is this interface for navigators, and then an efficient way to compose navigators, which I alluded to when I was showing the inline compilation. And every navigator that you've seen with all this very diverse expressive behavior is just an implementation of this interface. So it's very, very uniform. So again, it's an instance of this saying, uniformity enables composition, and composition creates leverage. We're going to keep seeing this over and over. Now, I've already talked about how p-states are just data structures, and so it's pretty natural to think that navigation would play some role in interacting with p-states. And that's exactly what it is. It's effectively a universal abstraction for querying and manipulating any data model because it's just so composable and expressive. I just want to show one example of what it looks like with using Rama. So here would be an example of URL analytics. So on the bottom is a p-state that is tracking the number of page views to a URL over time. So it's a map from a URL to a map from an hour bucket to the number of page views in that bucket. So if you want to know the number of page views over a range of time, you have to get all the buckets between those time ranges and sum them together. And you would do that in Spectre or in Rama with a path, which is just a Spectre path. And the path in this case, if you wanted to get the number of page views between hours 10 and 101 for url.foo.com, it would just be this. So you would do a select on the p-state. So you would run this code in your web server or in your REPL, just somewhere that's outside the cluster. And your p-state is living on the cluster in your deployed application. And so you would navigate to the url.foo.com and sorted map range. This is a navigator for sorted maps, which navigates to the submap containing all the keys and values between that range. So now we're navigated to a submap containing all the data of interest. Then you call view. View just navigates to the result of running that Clojure function on it. So vals just gets all the values of that map. So now we have all the buckets we care about in a one list. And then Rama has a little helper function, op/sum, that's just doing a reduce over the list to sum them together. And that gets you the results you want. And what's cool about this is that when you call this path gets sent to the server. It executes completely on the partition of the p-state that has the data, and all it sends back is that one number that you care about, right? And it's a lot easier than when you use a relational database and you have to write custom functions in some weird language and register them in some weird way. Here you would just use Clojure functions as needed. Okay, so the next topic is, and this is one that's really new to Rama, is the idea of co-locating computation and storage. But more than just like running your computation on the same node as where your p-states are stored, the idea here is to co-locate it in a way such that your events, that your code, has exclusive access to those p-states. That is, nothing else can read and write to them while your code is running. And what this does is it greatly simplifies concurrency and atomicity. And so this diagram here is basically a visual of the physical layout of a deployed Rama application. A Rama application is called a module, and a module is broken up into tasks. And every task contains a partition of all of your p-states and also all your depots. We'll talk about that more in the next section. And then it contains an event queue and an executor, like a thread, for running events off that queue. And when events are running, it's the only event running on that task. Nothing else can run until that event finishes, which means that event, like I said, has exclusive access to all the objects on that task. And what Rama does is it makes it really easy to write the code that actually runs on these tasks, and it makes it really easy to switch between tasks. So maybe your code needs to start on task 0, but then there's some data it needs from task 2, and then it needs to go back to task 0 or whatever your code needs to do. It depends on the application. Okay, so this is a pseudocode of what like programming Rama would feel like. You don't actually program events like this. Rama has something called data flow, which is unfortunately too big of a topic to fit into this presentation. That just kind of deserves its own talk. But this is effectively what you're doing with data flow. So let's say you have an event that you want to run that's and you're storing like funds, like money for users, and you want to change their funds by that amount. And you only want that to go through if that change would keep their balance above 0. And your code would look like this. You would find out by querying the p-state using a specter path how many funds do they currently have, and then you would see would applying this amount to those funds keep their balance above 0. If it's successful, then we'll change the funds. And then we'll also, in either whether it's successful or not, we'll also record in another p-state just the transaction attempt, what was the amount that was trying to be transferred, and then was it successful or not. So you can see it's doing a read, maybe one write, and then another write. But because we have exclusive access to the thread, we don't have to worry about race conditions. Because if we don't have to worry about another change funds event happening for the same user that could cause a race with the fact that we're both trying to read and write to the state at the same time. Because any other events have to be after us because we have exclusive access. And so what this does by having exclusive access is it completely eliminates the need for explicit transactions, row locks, isolation levels, and all the other stuff you have to deal with a database. It's much easier to what it lets you do is just think single-threaded, even though the system is highly parallel and concurrent. It just greatly simplifies what it takes to reason about these systems. You can still have race conditions, of course, but it's much easier to reason about. And what this lets you do effectively is you're just always just running arbitrary Clojure code all the time while reading and writing to co-located p-states, and just doing whatever business logic you need. I did want to show just what data flow code looks like, even though I don't have time to explain it, because as I said, it's a really deep topic. Effectively, what data flow code does is it makes distributed computation composable and makes moving around the cluster like a trivial thing to do. In the middle there, that's called a partitioner, and so that's an operation that switches what task we're running on. And as you can see, there's no callback functions here. You just read the code linearly, the code above it's running on one task, the code below it is running on a different task. And then all the code in between partitioners would run as an atomic event, and everything happening in that event is atomic. And this comes from an example from Rama Demo Gallery, which is an open source repository of Rama examples. Okay, so the last topic I want to talk about is interactive event sourcing. And actually, event sourcing already on its own is a big idea that's really impactful. Now, the reason I call this interactive event sourcing is just because the term event sourcing has a lot of baggage associated to it, which is not the fault of event sourcing, it's the fault of the people who attempted to use it. But the idea behind event sourcing is that rather than mutate the current state of the world, you instead capture a log, an append-only log of all the events that happened. And then you run business logic on top of that log, and then materialize as many views as you need that actually indexes the data and supports whatever queries you need. And, these are the kinds of examples of events that you might be appending to your log. And that first one's really interesting, a bank transfer event. Because if you're thinking in terms of relational databases, you're thinking in terms of effects. And so a bank transfer means you're going to modify the funds for one person, and you're going to modify the funds for a different person. So it's like two separate things that you're doing. But it's actually just one event. In event sourcing, it's all captured in one event that may have multiple downstream effects. So the atomicity comes from the fact that you're just appending one piece of data, and the fact that it has downstream effects is kind of orthogonal to that, if that makes sense. Now, there are some just massive benefits to event sourcing. First of all, you just automatically get a full audit trail and history of everything that's ever happened in your program. You can use that history for some really useful things, such as correcting mistakes. It's much easier to fix bugs that you may have introduced when you have the full history of everything that happened, because your buggy code is not trampling over your existing data. Or you can use that old data to make new views in the future, to support new features that you didn't anticipate. You have a ton of flexibility in how you consume the incoming data from those logs and the views that you create. And then this actually solves the normalization versus denormalization problem. And what this refers to is just a super common problem when using relational databases, and that a relational database is like it's trying to do two things at once, which are totally in conflict. It's trying to be a source of truth, and it's also trying to be an efficient index store for serving queries. And a data store cannot be both of those things at the same time in the same source of data. If you want to be a good source of truth, you should not store data redundantly, which means you should fully normalize. But if you do that, then you're inevitably going to run into a performance problem where your queries are too slow because they have to do too many joins to get all the things they need. So you have to denormalize, which means store data redundantly, and now you're not a good source of truth anymore. And so event sourcing solves this because it separates these components. The event log is unindexed, so there's no reason you can't have it fully normalized, and then you make as many views as you want because those are materialized from your log. Okay, so these are the traditional drawbacks of event sourcing, as I alluded to. And this is what a lot of people associate with event sourcing. It's very important as a programmer to learn to distinguish between the problems with an idea versus the problems with an implementation. And all of these are problems with implementations. They have absolutely nothing to do with the idea of event sourcing, which is very simple and very, very sound. But some of the issues you have with implementations would just be complexity from just having to run like so much more infrastructure, a queue, a processing system, and multiple databases. That's a lot of operational and also conceptual complexity that you have to deal with, because they're all independently managed systems. The second thing is that if your event source system is Kafka plus custom workers plus MongoDB and Cassandra, that's fundamentally asynchronous. There's no coordination between appending the Kafka and then the downstream effects. So that just makes it totally unusable for like an interactive consumer application, for example. And the last thing is storage bloat, because you're appending to the log, and also that data is also going to be materialized. So it seems like you're storing a lot more data. But again, none of these are about event sourcing. They're about the implementations of event sourcing. And so what Rama does, all it is event sourcing and materialized views integrated into one system, and just letting you just run arbitrary code for your business logic. It gives you full control over where your code is running. And then, as you saw with the materialized views, which are P states, it lets you, make as many P states as you need in as many different shapes as you need. And so all of those problems just aren't there with Rama, right? It's not complex to run because it's just one system with one coherent set of abstractions. It is not fundamentally asynchronous. Rama can be used for doing interactive consumer applications because it is integrated, so you can optionally, when you do your depot appends, you have various ACK levels that you can do. And by default, it's full acking. What full acking means is that the depot append only comes back not only when the depot append comes through, but also when all downstream effects have finished as well. And also your topologies processing can also return information about what happened during processing. So for example, you might have a depot append. You may have a depot which takes user registrations. Here we're trying to register username Alice with this password hash. And this returns the user ID that was computed for this user in some topology called core. Right? And the idea is that user ID would be a number if it was, if that username wasn't taken anymore, and it would be nil if the username was already taken and the registration didn't go through. Right? So this is totally usable for interactive use cases. Last thing is storage bloat. And so in general, you do want to keep all of your data just because obviously it's just so useful for all the reasons I alluded to. But there's also a lot of use cases where the data is coming in so fast, it's just, you just literally can't store it all. But again, because Rama is an integrated system, it knows what data has been processed, what data is needed, and what data is no longer needed. And so these depots can be configured to optionally auto-delete any fully processed data from the depot so that you're not forced to store so much data or deal with the complexity of trying to figure out auto-deletion yourself. Okay, so I've shown a number of technical ideas here which I hope have challenged you and expanded your mind to some extent on ways of thinking about these various programming topics. But more than these technical ideas, there's a psychological point I've been trying to make. Again, I go back to homoiconicity. The first time you saw homoiconicity, you were confronted with one of the greatest programming ideas of all time, and you couldn't see any of the value of it. And the thing about a programming idea is it's not just a tool with a how-to manual. Oftentimes, it's a different way of thinking about the world. And until you adapt your way of thinking, it's really hard to evaluate the idea, like at all. Now, the 5 technical ideas I presented besides homoiconicity probably provoked you in a similar way as homoiconicity did the first time you encountered it. And if you're able to understand the limitations of your brain and the need to adapt to a new way of thinking before evaluating and coming to a judgment about an idea, that's the difference between being someone who says things like, what's the deal with all the parens, and being someone who's able to leverage extremely powerful and impactful programming ideas. A few more things on Rama. So Rama is completely free to use, up to 2 nodes, which is sufficient for small and medium scale applications. You can go to our website to download, and then you can deploy it wherever you want. We also have one-click deploys for AWS and Azure, if that's where you run your infrastructure. Also on the website is lots of documentation, tutorials, use cases, and also you can sign up to our newsletter on the footer of the website. And the last thing is that I'm very active in the Rama channel on Clojurians, so if you have any questions while learning, I'm happy to help you out there. So that's all I have for you guys, and thank you very much.